Eh, Welcome. Big day today. We're going to start chapter 7, which is inference for numerical data. Okay. And so remember inference, by now we're so familiar with hypothesis testing and confidence intervals. And so what's really nice is we're going to just stay here with hypothesis testing and confidence intervals for a little while longer. And so that's nice because we already know a lot of the rules and now we need to be able to apply them to numerical data. Okay? And so that's going to be important because what do we know from chapter 1? Numerical data is data that we can say reasonably talk about the average, right? And so usually we're analyzing the average. Okay? And so we analyze the average or the mean. Huh? And so where we start in chapter 7 is with one sample mean, and we introduce a new distribution. Uh, This is our third distribution that we've seen so far, right? We've seen the Z distribution, we've seen the chi-squared distribution, and now we're going to have the T distribution. And so this is section 7.1, I should say. Okay. And so one sample mean with the t distribution. So when we're analyzing means, we use the t distribution. Okay. So it's really kind of nice, especially nice because the t distribution is very similar to the z distribution, right? And so knowing everything that we know about z, right, then that will translate in a similar way to the t distribution. Okay. Got some different slides. I brought in some old slides and because I didn't like the default ones. Okay. But so far, we've talked about inference, which is hypothesis testing, and confidence intervals for categorical data where we analyze proportions, right? Remember we talked about, so for proportions, for our sample, we have our p hat, so that's our sample proportion. And what do? We're trying to learn about p, which is our population proportion, right? We're going to have the same situation, right, for numerical data. And so when we analyze numerical data, then we usually want to analyze the mean, which is our x bar. So that's our sample mean, right? So x bar is our sample mean. And we're trying to learn about the population mean, right? Mu. Okay. So that's our goal. Okay. Just like we've done before, I want to show you on the formula sheet and talk about everything on the formula sheet, which is basically giving it all away. I know, but that's how I want you to see your formula sheet. It just gives everything away. Okay? And so if I go back to the full formula sheet, I did kind of pre-bake pre-bake our notes, and sort of. Um, so last day we did the chi-squared test of independence, and then below that we have our mini chi-squared table, and then here you'll see we have the one sample mean. Okay? So one sample mean is the newest type of question that we're going to talk about today. Okay? And it just is this. And at first glance, it should look familiar, right? Same layout as we've seen in the other sections for the other types of questions. Okay, but let's go to the blown up version. So one sample mean, um, what's this? This here, X bar, follows a normal distribution with a mean mu and a standard error of sigma over root n. So we're familiar with all those things. Okay? And so this is the central limit theorem for X bar. That's just theory, right? And you can just ignore it, okay? It's there because it's technically the basis of everything that we're doing, but we don't use it for our questions, right? They're all that information is all built into the formulas. Okay? We've got that similar problem though that we saw before, where we maybe had the central limit theorem referring to P's and Q's, right? But we don't have P's and Q's because those are from the population. So we've got the same situation here where it's centered on mu, which is your population mean, with a standard error of sigma, which is your population standard deviation over root n. I don't have mu and I don't have sigma, right? So what's my best guess, right? We use X bar as my best guess for mu, and I use my sample standard deviation S for my best guess for sigma. Okay? If I zoom in, if I'm trying to build a confidence interval for mu, okay, then I do the same thing that I have been doing, right? I take a point estimate, my best guess at what mu is, X bar. It's my best guess, okay? Plus minus, and then just generically some critical value, okay? So this will be our critical value, T star, with a little subscript n minus 1, which we'll get to. But for now, let's just take it at face value. It behaves the same way as Z. It determines the width of my confidence interval, right? Times the standard error, which is S over root n. So that's my best guess at what sigma is S over root n. Okay, so it has the same layout as before, right? A point estimate plus minus a critical value times the standard error of the point estimate. Okay. If we're doing a hypothesis test for mu, you might remember for one sample proportions, remember we had P equals P naught, but that P naught had to be a number from the question, right? The number we want to compare our sample proportion to. Okay? Now we have the same scenario, but for means, right? And so we'll have some number, mu naught, right? Some average that I want to compare my sample average to. Okay? And so mu naught where mu naught is a number that we want to, or is the number, I should say, where mu naught is the number, oops, oh, deleted a lot, number we want to compare our sample mean to. To compare our sample mean to. Right, and this will be from the question. So you'll replace that mu naught with some number. Okay. Otherwise, the same layout, right? I have to talk about the parameter, which is mu in this case, right? And I have to have an equal sign, right? We're going to always have an equal sign in our null hypothesis, and it's equal to some number. Okay. Then when we do our hypothesis testing, we still assume that the null hypothesis is true. And so then what we do for our t, and this is going to look very familiar, right, is we take our sample mean, how far is it from our hypothesized mean, divided by the standard error of x bar, right, which is s over root n. This looks like a z, right? And it's very similar to a z, right? And so, and if you think about the very first z that we saw, right? If we think about, let's see, z equals x minus mu over sigma, we've changed some things, right? X turned into x bar, right? And instead of sigma, so now my standard deviation for x bar is sigma over root n from up here, right? The problem is that because I don't know sigma, right, then it's not going to be a z anymore, but that's okay. So if I replace that sigma with an s, what happens is it turns into a t. Huh? And so there is that relationship there, right? But it's on your formula sheet, and so I would say just go with your formula sheet. Okay? Now, what we'll find with t is that just like the chi-squared distribution, the shape is going to depend on your degrees of freedom. Okay? And so what's nice is, of course, I tell you how to calculate the degrees of freedom. And for one sample mean, it's just going to be your sample size minus 1. Okay? And so we'll introduce that, but we've already seen that type of relationship with the degrees of freedom. And so yes, the t distribution, the shape of the t distribution is determined by the degrees of freedom. Okay? I was about to ask if there were any questions. It's just me here. Now, we know we have our conditions to check, okay? And I would say for means, the conditions are relatively simple, again, just like the chi-squared. And so as long as observations are independent, that's always one of them, right? But how can we, oh, it caught my thumbs up. But how can we make sure that they're independent? Well, I can, right, as long as I've randomly sampled, I can assume that they're independent. That's nice. Okay. And the population distribution is not extremely skewed. Okay. Then a large sample, okay, and so there's kind of, depending on what field you're in, how we pick what a large sample is kind of depends. I've seen as low as 15 sometimes, which is a little bit low for me, and so we're going to use any sample size bigger than 30 means that the sampling distribution is going to be nearly normal or approximately normal. Okay? And what that also means is that the standard error, s over root n, is reasonably reliable. Okay? And so, in short, what the conditions are, we have independence. Okay? Which means as long as we've randomly sampled, we can assume independence. If we have randomly sampled, we can assume independence. If we have not, if there's no note about, oh, it was a randomly selected sample of 56 people, for example, then what do you have to do? Then you have to say, I assume that these are independent of each other. Okay. And I gotta give myself a little bit more room here. Okay. And so then the normality condition, which we sometimes call the sample size condition, but the normality condition is two-pronged. Okay. If n is greater than or equal to 30, so if you have more than 30 in your sample size, we can assume normality. Okay. We can assume normality. There are kind of assuming it's not terribly skewed and things like that, because then you need a bigger sample size. But for us in this course, let's just keep it nice and simple. Okay. So what if the sample size is less than 30? That can happen, right? And so if n is less than 30, okay, we have to check the distribution and make sure that the distribution looks approximately normal. Okay, how do you do that? How do you check the distribution? Make a histogram. It's a nice place to start. Okay, so you can make a histogram and make sure that the distribution looks approximately normal. Okay. We check that the distribution, or I'll say the histogram just because that's what we should be using. We check that the histogram is approximately normal. Huh? So those are kind of the quick notes on the conditions. Huh? So the central limit theorem, which is that thing at the top that says x bar follows a normal distribution centered on mu with a standard error of sigma over root n. Okay. It says that the sampling distribution will be nearly normal, okay, for any sample size as long as the population distribution is nearly normal. So if you know that you're pulling from a normal distribution, then you can assume normality. Okay. That's really difficult to determine or to know, right? And so uh, you want to think about, okay, where did this data come from? And so do I expect this distribution to be symmetric, right? And would I expect to see lots of outliers, or would I be relatively safe thinking that, outliers are pretty rare? Like I said, we're gonna keep it nice and breezy right here with our conditions, especially for the normality. There are lots of ins and outs, but let's just keep it nice and simple. Okay. So the conditions summarized in a nicer way than how I wrote it. So the random sampling, right, that ensures independence. Okay. And so uh, this is your independence condition. Okay. So if the data come from a random sample of size n, then or a randomized experiment, if we're working with the experiments, then you can assume independence. Okay. The normality condition, the population has a normal distribution. That's a nice place to start, but not always reasonable. Okay. And so in practice, it's enough for the distribution to be symmetric and single peaked. Okay. And so when you're looking at those histograms, you want to be really kind of flexible. Okay. This one, I tend to skip this one. Okay, this one's optional. The population must be much larger than the sample. We've seen that in the n less than 10% condition, right? And so now we want to say at least 20 times as large, right? And again, that goes back to the independence, where if you've taken too much of a population, you will introduce some non-independent observations, right? But that's too much for us. Huh? Okay. And then we've talked about that. So like we saw in our from z equal to x minus mu over sigma, and then if we alter that to an x bar, then we have the standard error is now sigma over root n, but then we said, well, I don't know, oops, sorry. I don't know the population standard deviation because that's almost always the case. Because imagine this, so if you're pretending to know sigma, then at some point you had data on the entire population, and now you're trying to collect a sample to try to figure out what the entire population looks like. That's bonkers, right? And so we don't have sigma, but I do have my best guess, which is S. But what that does is it turns my Z into a T. Okay? And so they'll be related, definitely related, Z and T. Okay? And they'll look very similar and behave in the same way, which is nice. Okay? The T distribution is always centered at 0, okay? Just like Z. Okay? The distribution also has a bell shape, but the tails are thicker. Okay, and I've got an image on the next slide, I think it is. Okay, but so what happens is the tails are just lifted up a little bit more to make room for a little bit more uncertainty. Okay? Because there's more room in the tails, okay, observations are more likely to fall beyond 2 standard deviations from the mean than from the normal distribution. But that changes relatively quickly, so it's not even that big of a deal. Okay. And so what's the difference between these two? So the normal distribution, and that's our Z, right? That's our normal distribution. Notice how the normal distribution kind of drops down pretty quickly here, right? And approaches the axis quite quickly. Okay. Couple of notes. The total area under the curve is still 1, right? Because what is the area under the curve? It's a probability still, right? And so here, the area under the curve is a probability, and the total area is still 1. Okay. So what that means is when I make more room in the tails, right? And I like to do, I kind of like use my arms, right? And so when I start with a normal distribution of Z, right? And then I kind of make more room in the tails, then I have to flatten the top down, right? A little bit. It's not drastic, right? But it does flatten this T distribution down a little bit. And what we see here is that we have kind of these thicker tails. More area in the tails means what? Means the probability of seeing those more extreme values is higher, right? And so here, really what this means, so more area means the probability of more extreme T's, okay? More extreme T's is higher, right? So we tend to still use 2 as a rough guideline, um, but we can be a little bit more flexible, right? So for z's, we've said, okay, a z bigger than 2, usually we reject h naught, right? And so for t's, we can be a little bit more flexible, and of course we'll be able to calculate the probabilities using a table or software. Yeah. So as I mentioned, the shape of the t-distribution depends on the degrees of freedom. Okay? And so the degrees of freedom are n minus 1 for a one sample mean. Okay? And so the t-distribution has thicker tails for small sample sizes, and then the tails get thinner, so it actually moves, right? And so you start out with these big kind of fat tails, and then it gets smaller and smaller, and eventually approaches the z distribution. Okay? And so it depends on the sample size. Okay? And so here, I'll highlight this. The tails get thinner as the sample size increases. Okay? In fact, in fact, as n goes to infinity, or the population size, I should use the population size there, but let's just say infinity, then t is going to approach the z distribution. Okay? Or capital N, the population size. I like to think of it as infinity instead. Okay? So because it depends on the sample size, then the degrees of freedom are how we communicate the sample size to the t-distribution. Okay? And for a single sample, we have the degrees of freedom is n minus 1. Okay? And so what happens to the t-distribution as the degrees of freedom increases? Unlike the chi-squared distribution, which was quite different depending on the degrees of freedom, here for t with different degrees of freedom, it looks relatively the same, right? This thinnest degrees of freedom, or this thinnest line here, it's hard to see, I guess, but, or faintest line, uh, that's at 1 degree of freedom. That's huge. Or I guess that's small. What does that mean? If the degrees of freedom is n minus 1, then at 1 degree of freedom, you have a sample size of 2. Probably shouldn't do that, right? But even then, the t-distribution looks approximately normal, right? It does make room for this area in the tails, right? And so even a t of 6 at that point would not be considered that extreme because we're so uncertain with our results because I'm basing it off of a group of 2, right? So that's the idea. If I increase it to a sample size of 3, notice the drastic change, right? Just increasing by 1, right? And so, and I get slightly thinner tails, and then I have n equals 6 here. Okay, that's the next one, right? And so, another big jump, I think, right? And finally at 10 degrees of freedom, which means I have a sample size of only 11. That's very small still. Okay? But notice how close it is to the normal distribution, which is this top one. Okay? Right? So it's very close. And even if we look at the tails, right, they behave in a very similar way. Okay? And so even, oops, it's all jumpy. Even at a sample size of 11, looks kind of similar to a Z, right? So nothing crazy. Yeah. So we have not been using the Z table. You can, but we've been using that will not. Oops, gotta move that over. That will not be different for us. Okay. It's relatively new that I use the t-table so early, but I think it sets you up because then you only use one procedure for all your hypothesis testing and confidence intervals. And so I think it's a little bit cleaner. So we use the t-table to find the p-values. Okay. And so we've seen the t-table before. It's where we find our p-values for our z's, right? And our critical values for our confidence intervals. Okay. And because we've already, I'll skip this part because we've been using the t-table, right? But the difference between the t-table and the z table gives you an actual value, right? Up to a point. And whereas the t-table only gives you a range of values for your p-value, but we'll always be able to use that to draw our conclusion anyways, so it doesn't matter. We're familiar with the concept because we've been using the table already, but there are only positive values of t in the t-table. And so if you calculate a negative t-score, right, in step 2, do the test for your hypothesis test, then you have to drop the negative, right? Use the absolute value of it in the t-table. Now, I'm going to come back to these steps, but I do want to show that I have the t-table here. And so table C is the t-distribution of critical values. So far, we've only used the confidence levels, and then we've ignored all the rest. Well, today's the day we get to look at all the rest. Okay. And we've only worked with Z star and the one-sided P and the two-sided P. Okay. But what's the difference? Now we know degrees of freedom. Okay, degrees of freedom for our t is n minus 1. Okay, and so it's just your sample size minus 1, which means because your sample size doesn't change, right, once you have your degrees of freedom, then you're stuck on that line. Let's say you have a sample size of 16, just for simplicity. Then you have 16 minus 1, which is 15 degrees of freedom, and you're just stuck on this line. Right? Maybe if I do one that's closer, let's say we have a sample size of 31. Huh? Just so I can compare them between the 30 degrees of freedom and the Z star line. Notice that 0.683 is pretty close to 0.674, right? And 0.854 is pretty close to 0.841 and so on and so forth. And so these numbers are all going to be very similar. In fact, if you read down the line, right, what's happening? It's getting kind of a little bit tighter onto the Z. Right? And that's because the Z has the tightest tails. Okay. So there. Now we know what this entire table looks like. Okay. Which means that, kind of getting ahead of myself, but if you want to make a confidence interval and you need a T star, right? 95% confidence interval, you would use a T star of 2.042 as opposed to a Z star of 1.96. Okay. They're very, very similar. Okay. And we can use this line, this 30 degrees of freedom line, for example, to find our p-values, just like we did for the Z star line. Okay. Let's go back to these bullets here. So to find the p-value of a t-score, first you have to calculate your degrees of freedom. It depends on the type of sample or the type of question that you have, but for one sample, it's n minus 1. Now in the left-hand column, right on the side there, you'll find your degrees of freedom. And then you can't stray from this row because your sample size doesn't change. I will make a note here. If the degrees of freedom is not listed, we always round down the degrees of freedom, which I guess is physically up on the table. So if the degrees of freedom is not listed, you round down to the nearest degrees of freedom. And I should say listed. Going back to our table, it might be nice if you have a table. These tables are posted on Moodle if you want an electronic copy. Starts off 1 through 30. They're all listed by ones, and so anything up to 30 is going to be listed explicitly, so then you don't need to do any rounding. It's when we get to this point here. Oops. Not Z. Oy. It's when we get to this point here. 30 jumps to 40, and then 50, and then 60, and then 80, and then 100, and then 1,000. And so if we have, for example, let's do a tricky one. As an example, if the degrees of freedom is 59, that means you have a sample size of 60, but you have to use 50 degrees of freedom. Because what would 60 degrees of freedom say? Well, that's pretending like you have a sample of size 61, but you only have a sample of size 60, which is picky, yes, but that would be lying, right? And so then you would be claiming that your results are more stable than they actually are, right? Or more reliable. Okay. And so you always round down. Would need to use degrees of freedom equal to 50. Okay. I'll make a note on here as well. So if the degrees of freedom is not listed, round down. Okay. Even if you have 900 degrees of freedom, then it's tempting to go to 1,000, but that would be really bad. And the difference between 100 in terms of these numbers and 1,000 is minimal, right? So even though it feels painful in a way, just go for the 100. Okay? If you have 900 degrees of freedom. So find your degrees of freedom, and if it's not listed, then you have to round down to the nearest degrees of freedom that is listed. Now, you're going to move along that row to figure out where the absolute value of your calculated t from step 2 in your hypothesis test would fall. This is to find the p-value, in case I didn't say that. I feel like I didn't. Now, you should have your 2 fingers on 2 t-scores that wrap around your calculated t, and you should record them, just like we were doing for z, right? The absolute value of t now is between the lower t and the upper t. So you have to write those down to show your work. Now, move your 2 fingers down to the bottom. Okay. This is where we have to go back to the alternative hypothesis. You'll know if you have a one-sided or a two-sided test. How? Because, if the alternative hypothesis is that mu is not equal to some number, that not equal to tells me that I'm interested in both sides. Okay? And so that's what we call a two-sided test. Whereas if the alternative is that mu is less than mu naught or mu is greater than mu naught, then I only care about one of those sides, right? One at a time. And so that's what we call a one-sided test. Okay. So depending on if you have a one-sided or a two-sided test, right, then you have to use the appropriate one-sided or two-sided p-value, which you read from right to left, right, since it's still decreasing as you move out. Okay. And you're going to record the range of the p-values that you found, just like we've been doing, right? And so usually I like you to say the two-sided p-value or the one-sided p-value, just to emphasize that you know what you're doing, is going to be between 2 values. And make sure you list them from smallest to largest. Yeah. And then of course from this range of the p-value, then we can compare it to the alpha level and decide what our conclusion is, right? If it's less than 0.05 or the alpha level in general, then you have enough evidence to reject H0. This might be a good time. If it feels like, these p-values, I know I should know what they are, but do I actually know what they are, or just it's okay, right? It's still okay if you feel like I don't know what this thing is, as long as you're going through the motions and you're able to kind of work through finding the p-value. Understanding what it is at this point is not necessary. I hope that soon you will. Okay, but if you want to ask me about a p-value, just know that it's not too late. We can talk about p-values because they're notoriously difficult to understand. Okay? So it's okay to stick with it. Okay, let's do a hypothesis testing question. So jumping right into, so we've laid all our groundwork, we've got our formula sheet taken care of, we've got our conditions, we've got the t-table under control. So let's see this thing in action. We'll start with a hypothesis test just because it's kind of the longer version, longer thing to do. Okay. The level of dissolved oxygen, which is abbreviated DO, in a stream or a river is an important indicator of the water's ability to support aquatic life. So, of course, that's a common measurement. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. And here are the results in milligrams per liter. Right? And so 4.53, 5.5, 4.01, we've got this this variation, but generally hovering around 5. Okay. So the mean and the standard deviation of the sample are x bar, which is 4.77, and s, which is 0.94. Okay. And so if we calculated the mean and the standard deviation of these numbers, that's what we would find. Okay. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. So that would be really bad. Is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? Here we go. I'm going to start and tackle the step 0, the conditions. Check the conditions. The independence condition. It says that they were randomly sampled, right? And so that's good. So usually how we write it is just randomly sampled. Check. Nice and easy. Which means I can assume independence. The normality condition, n is 15, right? We only have a sample of 15 randomly chosen locations, and so we only have 15 measurements. That's okay. N is 15, which is less than 30. So what do we have to assume then? So we must assume that the distribution is approximately normal. We assume the distribution is approximately normal. We could make a histogram of the measurements and check it. I don't have that, and so then I just have to go ahead and assume that it's approximately normal. I'll do a little note here. Could make a histogram to check. We're not going to, but you could. Okay. Step 1 of the hypothesis test. Why do we know it's a hypothesis test? Because we want to know, is there evidence? As soon as I need evidence, I have to do a full hypothesis test. So step 1, state the hypotheses. And what I'm going to do is just go back and grab from the formula sheet here. We're doing a hypothesis test. So step 1, step 2. And you need the degrees of freedom for step 3. Step 1, the null hypothesis is that mu is equal to mu naught. Now remember, mu naught has to be a number, right? A number that I replace with a number from the question. So my null hypothesis, mu is equal to some number. Now that number is the number I want to compare my sample mean to. So my sample mean is 4.77. We're also told that if it's below 5, then we're in trouble, right? And so that number that I want to compare 4.77 to is 5, right? I know 4.77 is less than 5, right? So it is below 5, but what we're trying to find is if it's significantly less than 5, right? There's some wiggle room around 5, okay? So this is mu equal to 5. Okay. Whereas the alternative hypothesis still has to talk about mu and how it relates to 5, right? But I need to change the sign depending on what the question is. And so mu, how it relates to 5, and I want to know if it's below 5. So is mu less than 5? Then I'm in trouble. Okay. I like to make a note here that this is going to be a one-sided test, right? Because I'm only concerned with one extreme. It seems that a dissolved oxygen level extremely high, higher than 5 is fine. Okay? And so this is a one-sided test. Then we're ready for step 2, do the test, which is technically calculate the test statistic, but that's boring, right? Do the tests, do the do. Huh? Now, from your formula sheet, the test statistic is going to be a t. Huh? X bar minus mu naught divided by s over root n. T is x bar minus mu naught divided by s over root n. Okay. Nice. I have all those numbers, so let's just plug them in. T is 4.77 minus 5, right? How far is 4.77 from 5? If I take into account the standard deviation, which we're told was 0.94, divided by the root of n, which was 15. So 0.94 divided by the root of 15. Okay. You'll want to be really careful here with kind of how you do your calculations, right? And so I will write out every step, or not every step. I'm going to first calculate the standard error, simplify that. But if you want to just go through, that's fine, as long as you end up with the same answer as I do. Okay. So doing them separately or simplifying separately, 4.77 minus 5 is, oops, t is negative 0.23 divided by a spread of 0.94 divided by the square root of 15 divided by 0.2427069564 and negative 0.23 divided by that guy. I find that t is going to be negative 0.9476448613. For t, to match the t table, we need to keep at least 3 decimal places. Yeah? And so t here is going to be negative 0.948 to 3 decimal places. Right? You want to keep as many as you can, but I know you guys are keen to round, so you have to keep at least 3 to match the table. Which is our next step. Step 3, find the p-value. To find the p-value, we have to use the t-table. Now, let's see here. We need to use the t-table. We need to find the degrees of freedom. And so the degrees of freedom is n minus 1. Right? And that's from up here, where the degrees of freedom is n minus 1. Okay. So your degrees of freedom is 15 minus 1. Oops. So your degrees of freedom is 14. Now, usually I just kind of write across the page. I'm trying to do it properly. Because writing across the page for your equations is kind of sloppy. Now what? Using the t-table, right? And as soon as I catch myself doing something, then I'm going to write it down, right? And so I encourage you to do the same because that communicates to me how you approached a problem, right? And so using the t-table, with degrees of freedom equal to 14. And 14 degrees of freedom is in the table, so we're going to use that. We find, and did I do, of course, we find the absolute value of t equal to negative 0.948 is between two values. Okay, what two values? Let's see. So once I have decided that I have 14 degrees of freedom, then this is where I'm stuck, right? I'm stuck on this line, and I had 0.948 that I'm going to try to place here. So I start here at 0, 0.948, looks like it's between 0.868 and 1.076. I'll take a little screenshot here, maybe this many, copy. Paste image. And so we find that RT is going to be somewhere between these two values, 0.868 and 1.076. That is going to translate to our p-value, which is really what we're after. Now remember, and this is why I make a note at the beginning here, because it feels like a long time ago, we're doing a one-sided test, and so I need the one-sided p-value. So then the one-sided p-value is between two values. Let's see where it is. So I'll use my pointer, but I use my two fingers and I drag it down, and my one-sided p-value is going to be between 0.15, right? Start on this side, and 0.2. And I'll do this. Hey, didn't do it. Copy. So the one-sided p-value, and you have to read them from right to left, right? Because they're decreasing as you move out, which means as long as you keep your inequalities the same, right? Which I like to do because then you just list them from smallest to largest. And so then we get 0.15, 0.20. So quite a large p-value. Move this up a little bit. From the p-value, we're ready for our conclusion. Now our conclusion stays the same, right? It's a big conclusion, it's a lot of components, but it's always going to be the same for all these types of hypothesis testing questions, right? And so we follow the same format, which is I have to compare my p-value to the alpha level, right? What does that mean in terms of my null hypothesis? Do I have enough evidence to reject it or no? And then finally, what does that mean in terms of the question? So step 4 is my conclusion. And here we go. First, I want you to tell me everything that you know, right? Show off all your knowledge. So since our one-sided p-value is between 0.15 and 0.20, it is not less than our alpha level. And I think we were told an alpha level. Let me just confirm here. Aha. If if there was nothing stated, we would assume 0.05 anyways. And so, but here it is stated, so you just want to check to make sure that you have the right one. So since our one-sided p-value is between 0.15 and 0.20, it is not less than our alpha level of 0.05, which means we do not have enough evidence to reject H naught, which means we do not have enough evidence to reject H naught. Okay. What does that mean in terms of the question? Let's go back. A dissolved oxygen level below 5 puts aquatic life at risk. Which means here, if we had rejected H naught, then that would be really bad, right? Because the alternative hypothesis is that the aquatic life is at risk. So this is one of those rare scenarios where we're actually kind of hoping to not be able to reject H naught. So that's great news. Therefore, there is not evidence that the dissolved oxygen level is different from 5. And maybe I should say is less than 5, just to match. Or some version of that, right? So, is there evidence that the aquatic life is at risk? No, there isn't. So maybe that's what I should say. Therefore, there's not evidence that the dissolved oxygen, I'll put this in brackets, that the aquatic life, oops, how do you spell aquatic? Not starting with a Q, probably. Aquatic life is at risk. Let's see if that's better. Therefore, there's not evidence that the aquatic life is at risk, or if you prefer, the dissolved oxygen level is less than 5. Which is great news for all the fish. Nice. Perfect. Good. So, same procedure, right? Just slightly different calculations, slightly, right? We're calculating a t, which requires the t table and the degrees of freedom, but besides that, I mean, basically the same. What if we have to do a confidence interval example? This one's not as cute, but it's nice to see multiple questions, right? Especially for when you're trying to learn what a typical one sample mean type of question looks like. Business bankruptcies in Canada are monitored by the Office of the Superintendent of Bankruptcy Canada, OSB, which hopefully that's still true. I wrote these a long time ago. Included in each report are the assets and liabilities the company declared at the time of the bankruptcy filing. Okay. A study is based on a random sample of 75 reports from the current year. The average debt, which is the liabilities minus the assets, is $92,172 with a standard deviation of $111,538. Ugh. We want to construct a 95% confidence interval for the average debt of these companies at the time of filing. Okay. Now, what are we given here? unlike before, we have to kind of pick out. So the question earlier said X bar is this and S is this. And so I was kind of holding our hands a little bit, right? And so a study is based on a random sample of 75 reports. So that means that my N is 75. The average debt, so the average, which is your X bar, is 92,172. And the standard deviation is 111,000, blah, blah, blah. So we'll call this S. And I want to construct a 95% confidence interval for the average debt of these companies at the time of filing. I'm going to add a page here. We can check the conditions. And they're relatively simple. In fact, we didn't really celebrate this earlier, but hypothesis testing questions and confidence intervals for means have the same conditions. And so that's nice. Again, like the chi-squared, we have the same conditions that we need to check, unlike proportions, right, where we have different conditions that we check depending on what we're going to do. And so here to check our conditions, it's the same as the hypothesis testing conditions. That's nice for means. So the independence condition, well, we're told that it was a random sample. So I'm just going to write random sample, check mark, done. Because a random sample means I am allowed to assume that the observations are independent of each other. The normality condition, N is 75, which is greater than or equal to 30. So we can assume normality. Nice and breezy. Okay. Now, we wanted to build a confidence interval. So from the formula sheet, I'm going to go back and just grab the confidence interval here. We have our X bar, we have our S, we have our N, we need our T star. Now this N minus 1 is just saying at N minus 1 degrees of freedom. And so this here just means T star at degrees of freedom equal to N minus 1. Little note there. So you can ignore it. Because we have the same degrees of freedom as before, right? And so N minus 1, same as before. So let's find our degrees of freedom first. N minus 1. And like I said, usually I write across 75 minus 1 is 74. Let's go to our T table because our goal is to find this T star at 74 degrees of freedom. So my degrees of freedom here, going down, trying to find 74. I won't find it. It's by design. I'm stuck between 60 and 80. But remember, you can't round up, right? So you have to use 60. Okay? And if you're making a change, right, like using 60 instead of 74, if you had software, if you're using Excel, you can use 74, right? And so, but for the table, we have to round down. So what I want you to do is make a note. So here, but using degrees of freedom equal to 60. That's to show me that you knew to round down and you knew to use 60. Right? So T star at 60 degrees of freedom for a 95% confidence interval. Let's go find it. What do you think it's going to be close to? Should be close to 2, right? Just as it was before. Wow, I can't believe our luck. Exactly 2. Nice. Oh, and I should screen grab that. Nice. So now I'm ready to construct my confidence interval. Right? X bar plus minus T star times S over root N. Notice how I've dropped the subscript. Oh. X bar was 92,172. Plus minus 2.000 times S, which was 111,538. Let's see if I can remember that. Divided by the root of N, which is 75. One heads up here is N is always 75, right? So N is still 75. It's the degrees of freedom that you have to round down. I see that quite commonly, right? You remember you have to round something down, but don't round your N. N is still 75. Huh? Now, let's see here. 111,538 divided by the root of 75 times 2. Let's just go for the margin of error right away. 25,758.59773. This is money, so I'm just going to go ahead and round this to 2 decimal places right away, because then I don't have to carry my decimals. Or 92,172 plus minus 2575860, right? 2 decimal places for money. Oops, money. So my interval looks like this: 92,172 minus 25,758.6. I get 66413.40. 92,172 plus 25,758.6. 117930 and 60 pennies. That's only half the work for the confidence interval, though, right? We have to interpret the confidence interval, right? And so let's see, what does that mean? Do a little, so many commas in there. Show that it's dollars. Means that we are same blurb, same confidence interval blurb that we've been using this whole time. It doesn't change. Okay. We are 95% confident because we made a 95% confidence interval. We are 95% confident the interval from $66,413.40 to $117,930.60 captures what? This is where you reword the question as an answer. Construct a 95% confidence interval for the average debt of these companies at the time of filing. So captures the average debt of these companies at the time of filing. The average debt of these companies. I'm taking issue with these companies, but I just want you to reword the question as an answer, so we'll ignore it. Captures the average debt of these companies at the time of filing. Nice. Okay, good. So that is one sample mean. Now you've seen a hypothesis test. Well, you've seen the t-distribution introduced, right? You've seen a hypothesis test. You've seen a confidence interval. Now, what I would like to do, and I'm just kind of checking the time here. I can't really remember when I started though, but I think I have some time. Because what I want to do is just talk about paired data, which is the next section, 7.2. Because, spoiler alert, it ends up being the same as what we just did. Okay? And so, with a twist. So, let's introduce it now. Paired data is exactly as it sounds. Okay, so pairs like this, when we have two numerical measurements from the same subject. So in the same row, you have two numerical measurements. Okay, that's technically two samples, right? So two numerical measurements in the same row is technically two samples. Okay. But when they're from the same subject, right, that makes them paired. Okay. There are kind of extreme situations where they're not necessarily on the same subject, but similar subjects. And so then you want to treat them as pairs, such as if you have twins, right? You've done measurements on twins, then you treat them as pairs still. Okay. Another common example for paired data is kind of before and after scores, right? I get you to write a test, and then I teach you some things about those topics, and then you do the test again and see how you improved, right? And so the before and after scores, or there's lots of different different examples, but those are kind of common examples. Another common example is something like this one. So paired observations, if you have 200 observations that were randomly sampled from the high school and beyond survey, so a survey they do in the States. The same students took a reading and a writing test, right? So two different tests, and their scores are shown below. At first glance, does there appear to be a difference between the average reading and writing scores? I would say my gut reaction is not really, right? If I compare this distribution to this distribution, the writing scores seem to be have less variability, right? So I'm expecting it to have a smaller standard deviation, right? But in general, they seem very similar, right? I can see that the median score for the writing is slightly higher than the reading score, right? But I also get slightly higher scores in the reading than I do for any of the writing scores, right? So that's what we're going to try to figure out is how do these two compare? Uh, The pickle is that the same students took a reading and a writing test, and their scores are shown below. Okay? Now, the question is, are the reading and the writing scores of each student independent of each other? They're not, right? Because they're paired. Independent of each other. No, they are paired. That's okay. It just is how we identify this type of data, right? This type of question, paired data. If you have this paired information, we'll know how to deal with that. And so that's what we're introducing here. So how we show that, so each student has some generated ID number, doesn't mean anything, we don't analyze it, right? And we get their reading scores and their writing scores, right? And so what we tend to see is that if the reading scores are high, I expect the writing scores to be high as well, right? Whereas if I have a reading score that's low, I expect the writing score to be low as well, right? And so that's what pairing these observations does for us, is it eliminates kind of that variability between the different students, right? And so we're able to capture the difference within each student. Okay, and so that's the beautiful part about the paired data. Okay? So, well, we already said no here, but I think it's on the next slide. Okay. So what's really fun about paired data is, well, when you have two sets of observations, right, that have this linkage, this pairing, this special correspondence, which I'm going to just call pairing or pairs. I guess it's introduced here, but whatever. So if they're non-independent, then we call them paired. Okay? If they're not independent, that's okay, right? We have two measurements from each student. The independence condition still has to hold that each student is independent of the next student, right? So I'll point that out in a bit. To analyze paired data, then what we do is we look at the difference in the outcomes of each pair of observations. So for example, we calculate the difference, which is the reading score minus the writing score for each individual. Of course, you don't want to mix up how you're subtracting, right? You have to use a consistent order. In fact, I always use the first one minus the second one, just because it's easier. Okay? But notice here, what happens? Now you've captured all this activity in the reading and the writing scores in one sample of the differences. We now have one sample of differences. In fact, we can take this data, this sample, this one sample, and we could make a histogram. It looks approximately normal, and so I'm happy with that, right? And so we can look at the distribution of the differences and notice that they're centered on 0. Okay, that's going to be useful. So our parameter of interest, so the thing from the population that we're interested in, is going to be the average difference between the reading and the writing scores of all high school students. Now, how we denote that is with a mu diff. The point estimate is the average difference from the sampled high school students, and how we denote that is with the x bar diff. Okay. Now we just put that little diff on there. Sometimes we just use a D, but that can look like other things. So it can look like a 2 sometimes. So I write diff, okay? And it's just to emphasize that, hey, this is the population mean of the differences. So here, this is the population mean of the differences. And this is the sample mean of the differences. We can also calculate the standard deviation of the differences. Okay. We can also calculate S diff, which is the standard deviation of the differences. And of course, we'll have the number of differences, n diff. N diff has to be the same as the number of observations that I have, or the number of rows that I have, right? So even though, yes, technically we have 2 samples and I have 200 in each sample, right? You want to focus on the fact that we've just summarized it as the differences. Okay. And n diff, which is the number of differences. Okay. So to get to our hypotheses, let's think about this. If there was no difference between the scores on the reading and the writing exam, so if they're the same, 57 and 57, let's say, then the difference would be 0. And the same thing would be true for the average, right? So then you would expect the average difference to be 0. And I did change this because it seems to have copied, I don't know, they copied from the wrong question. And so when we develop our hypotheses, right, for testing if there's a difference between the average reading and writing scores, then how we communicate that the average reading and writing scores are equal is that mu diff is equal to 0. Right? Versus if we want to know if they're different, then we want to set mu diff is not equal to 0. Okay? What's really nice about paired data, once you've decided you have paired data, then this will always be, this is always, oops, H naught for paired data. So that's nice. If you read a question and you say, hey, this is paired data, you know your null hypothesis, which should say like this, is going to be that mu diff is equal to 0. And your alternative depends on the question, but usually we have not equal to 0, just because it's hard to talk about the mean difference being less than 0, for example, right? We'll have an example, but I'll save it for in class. So usually we use a not equal to in our alternative hypothesis for paired data. Okay. So as I already spoiled for us, right? We're not going to change a thing, okay? Because we boiled it down to 1 sample, right? Now I have a 1 sample of differences and I want to analyze the mean. Yeah? And so we're testing to see if the average difference is different than 0. And which of the following is true? I'll skip to the next one. It's A, but let's talk about all of them. So since students are sampled randomly, so that's good. That means they're independent. Okay. Okay. and are less than 10% of all high school students, again, the independence, but kind of optional, we can assume that the difference between the reading and the writing scores of one student in the sample is independent of another. That's true. The distribution of differences is bimodal. Well, we saw from the histogram, remember the histogram looked approximately normal, right? If it was bimodal, then technically you should proceed with caution, right? And so I'm going to say this one's false. In order for differences to be random, we should have sampled with replacement. That's not true. That's just not true. I want to talk about why this last one is not true. Okay? Since students are sampled randomly and are less than 10% of all students, notice that this is the same as what we had in A, right? We can assume that the sampling distribution of the average difference will be nearly normal. But that's not how we check normality, right? And so this is the problem. To check if it's nearly normal, we need n to be greater than or equal to 30. It is nearly normal. It is nearly normal since n equal to 200, or n diff, I should say, equal to 200 is greater than or equal to 30. Okay? So then we can assume normality. And so that's why. Okay? It's not because they were sampled randomly. Okay? Nice. So there. Good. Let's see an example. What does this usually read like? The observed average difference between the two scores, and we're talking about the same example, right, is negative 0.545 points, 0.545, yeah, points, and the standard deviation of the difference is 8.887 points. Do these data provide convincing evidence of a difference between the average scores on the two exams? Use an alpha level of 0.05. Okay. So the average difference, that's your X bar diff, is negative 0.545. And the standard deviation of the differences, oops, S diff is 8.887. And we also know that N diff is equal to 200. And we want to do a hypothesis test. We checked the conditions above. So here's step 0. Check the conditions. I'll just do it briefly. And so the independence condition, students were randomly sampled. So what that means is the differences are all independent of each other, right? But it's listed more thoroughly above, so I'm just going to use the brief version. To check our normality, we said that, okay, well, N diff, which is 200, is greater than or equal to 30. So we can assume normality. Great. Now we're ready. Now I haven't brought in the formula sheet yet because it's going to look the same as what we saw for one sample mean. So here we had everything for one sample mean, and now Last column of our formula sheet. It's a big day today. Copy. Paste. Okay. We're talking about paired data. Sometimes we call them matched pairs. I like to call them matched pairs, sometimes just to emphasize that they're matched on the observations. But we're analyzing the mean difference, okay? And I want to emphasize that because if we go back to the formula sheet, the next section shouldn't be a surprise at this point, is where we analyze two sample means, two independent sample means, where we analyze the difference of two means. Notice the difference here, the mean difference, right? The average of the difference versus the difference of two means. Okay? But we're working here today. If I want to build a confidence interval for mu diff, x bar diff plus minus t star times s diff over the root of n diff, that's the exact same formula that we just had. We just have little diffs everywhere, right? Sprinkled everywhere. Hypothesis test for mu diff. Like I said, the null hypothesis will always be that mu diff is equal to 0. Okay? Which brings us to our t, our step 2, our test statistic, x bar diff. How far is it from 0? That's always the case, right? So usually we don't even write the 0. I just wanted to show you that it was there. Divided by s diff over the root of n diff. And just as before, the degrees of freedom is going to be n diff minus 1. So, nothing to it but to do it. Here we go. Step 1, state the hypotheses. Now, because I've decided already that this is a paired data question, I know that mu diff is equal to 0. Huh? Which means my alternative has to talk about how mu diff relates to 0. And from the question, I want to make sure that I get the right sign. Now, do these data provide convincing evidence of a difference between the average scores? So I want to know if they're not equal to 0. Which makes this a two-sided test. Huh? Good. Step 2. Do the test. T, right? Step 1, step 2. Use it for step 3. Says T is x bar diff. How far is it from 0? Taking into account the spread of s diff divided by the root of n diff. Page here. So T, we have our x bar diff, which was, I want to say negative 0.545 minus 0, divided by 8.887 divided by the square root of 200. Let me just confirm those numbers here. Negative 0.545 and 8.887. Good. Nailed it. Now, 8.887 divided by the root of 200. I get a t of negative 0.545 divided by 0.628405796.4. So t is going to be negative 0.545 divided by that. I get negative 0.8672739.862. So t to 3 decimal places, because you have to keep at least 3. 0.867, 3 decimal places. That's to match the table. You don't have to memorize that. You can just look at the table and say, oh, I need to match it. Now, step 3, find the p-value. Let's see here. We need our degrees of freedom, which is n diff minus 1, which is 200 minus 1, which is 199. Now I know 199 is not on my table, right? So I'm already going to start, but using degrees of freedom equal to, I know it's 100, but I'll show you why. This new question. Oops. So I had 199 degrees of freedom. I'm choosing between 100 and 1,000. Well, I have to round down, and so that's why it has to be 100. So I have 100 degrees of freedom. And what you want to do is on this line, we have to try to place the absolute value of our t. Now I'm just going to grab this, copy, so that we have it. All right, so using 100 degrees of freedom, okay, we find the absolute value of t equal to negative 0.867, oops, absolute value, is between 0.867 is between these two values, 0.845 and 1.042. Now remember, we want to find the p-value now, right? And so the p-value, we had a two-sided test, right? And that's why I make a little reminder up here, right? You can go back and look, two-sided test. Okay, so I need a two-sided p-value. So my two-sided p-value is going to be between 0.30 and 0.40. Okay. Nice, quite large. Conclusion time. Step 4, conclusion. Since our two-sided p-value is between 0.30 and 0.40, it is not less than our alpha equal to 0.05. We were told to use an alpha level of 0.05, which means we do not have enough evidence to reject H naught. Oops. Not have enough evidence to reject H naught. Therefore, there's no difference in the average reading and writing scores. Therefore, and I'm just going to cheat here, and oops, only need this, copy. Therefore, these data do not provide convincing evidence of a difference between the average scores on the two exams, period. And as my last little tidbit, so here on the next, so that's the end of the hypothesis test. Now, we've already talked about the p-value and things like that, but what I want to follow up with, if you were to construct a 95% confidence interval, would you expect the interval to include 0? You would, right? Because we found that we didn't have enough evidence to reject H naught, right? Yes, since we did not reject the null hypothesis, which said that mu diff is equal to 0, right? So there's that link. Now you can try it. They use only 2 decimal places for the critical value, but other than that, you can build a confidence interval and interpret a confidence interval. But I think what we'll do for review is we'll do this one together for review next day. All right, that's the end. Good job. And let me stop this.